Good afternoon. This is not a physics lecture, but of course contains some physics, as you can imagine. And this is done in conjunction with the assigned reading from Hawking's Brief History of Time. Of course, it doesn't just discuss what is in those chapters, but goes quite beyond. The main aim is to give you a general idea about the very important conceptual changes that took place in our understanding of nature, at least the physical part of nature, during essentially the 20th century. In fact, as we celebrate AUB's 150th anniversary, we can also celebrate the unification of electric and magnetic forces by Maxwell in around the same time as AUB was founded, that led to his prediction that electromagnetic waves must exist. It was also seen later that light, in fact, travels as an electromagnetic wave. Now, you use electromagnetic waves every day in your life, and you watch TV and so on, but it's important to recognize that, in fact, prior to the establishment of AUB, nobody knew of their existence. As a matter of fact, we can also this year celebrate effectively the 100th anniversary of another very important discovery by Einstein, referred to usually as the general theory of relativity. As I will show you a little bit later on, what Einstein did is remove the concept of a force of gravity to say that, in fact, there is no such thing as a force of gravity, but that we all move in what we call curved space-time, which is the same thing. So what I will do in this lecture is try to briefly go over some of the main concepts. So what we will do is to try to understand the so-called nature of time and space. We will see that gravity is a property of space-time curvature, that is bending. We'll also see an overview of the standard model of interactions of radiation and matter, which is related to quantum mechanics and quantization. And then the combination of all of the above would lead basically to the understanding of what we now call a theory of the origin of the universe from a physical point of view, at least. So this is. The historical milestones are, in the past, we start with the Aristotelian universe, which says that everything revolves around the Earth as the center of the universe. Of course, with the idea that we humans are at the center of the universe and everything is made for our own benefit. And then this theory of Aristotle was expanded upon by Ptolemy. Then it was Copernicus who first suggested that, well, maybe we're pushing it too far. The universe doesn't all rotate around the Earth, but maybe everything, all the planets, including the one we live in fact, rotates around the sun. And it was later Kepler who discovered that, in fact, by observation, that this, in fact, is true, and that the orbits that the planets make around the sun are ellipses, also not quite circles. All of this above information was used by Newton to set up what he called the theory of gravity and Newton's laws of motion, which, as you know, all is summarized by one formula called F equals ma that I'm sure you've seen somewhere along during your high school and so on. On the other side, Coulomb was investigating electrostatics, Ampere, currents and magnetic fields, Faraday, time-changing fields, electric fields, magnetic fields, and then Maxwell, as I just mentioned, essentially set up Maxwell's theory, which unified all these forces together. So in a sense, by the year 1900, we had two very important laws of nature, Newton's laws of gravitation and the equations of motion, and then Maxwell's equation, which relate to electromagnetic interactions. At that time, many people thought that physics has been done, finished, there's not much more to be discussed. Little did they know, because in fact, it was I'm sorry, I'm not used to this, but it's just, okay. Newton's laws, you know, Coulombs of electrostatics are similar. And all of this is set up in what we call a classical space-time. Classical space-time is the way we experience it every day. Space is absolute, flat, and time, of course, seems to flow forever from no beginning, in a sense, to no end. And in a sense, all physical phenomena are somehow described by events that take place in this stage of space and as a function of time. So you can follow things as they move along. And what Newton did and Maxwell did was to tell us how do we follow any object that is moving if it is subjected to forces, or if we have electromagnetic forces, also what happens to them and to electromagnetic waves and so on. Now, generally speaking, when you stick to this picture, and from our everyday experience, we know that velocity is a relativistic concept. So for example, if you're standing still, you can see that somebody is moving relative to you. However, if two objects are moving, you also experience that, say, if you're driving your car and there's another car coming towards you, you have the sense that the other car is moving faster than normal. And if it is moving along in the same direction as you're moving, if you forget that there is space around you, you might think that you and the car are actually at rest relative to one another, although you might be moving. In fact, as we sit here, you know very well that we are moving around the sun. And in fact, we move around the sun and come back here every year once. So although we are moving, we don't perceive ourselves as moving relative to each other because we are all moving in the same direction. The formula V2 equals V1 plus V is usually what you learn in elementary physics as the way you add velocities, meaning if you know the velocity of one object and you happen to be moving, you can calculate this. And without going to details that these are vector quantities and so on, let's just take it as is. However, when you look at Maxwell's equations and this electromagnetic wave that he predicted, implicit in it is the fact that the electromagnetic wave in vacuum has a well-defined fixed speed. It doesn't seem to follow this relationship V1 equals, or V2 equals V1 plus V. That is, if you actually observe light, whether you are standing still or whether you are moving, or whether the source of light is moving or standing still, try to measure the velocity of light, you'll always get a number, which is this fixed number C. Using this idea, Einstein basically wanted to see why is it that ordinary objects somehow have different velocities as we measure them when we are moving or standing still, whereas light does not. So to him, the speed of light is constant, but somehow, which is a basic thing from Maxwell's equations, that is inconsistent with what our normal everyday experience tells us. So somehow light behaves differently than everything else. At about 1900, other physical phenomena had led Mr. Planck, another physicist in Germany, to suggest that somehow light is not only a Maxwellian, if you like, electromagnetic wave, but somehow it appears to come to us or to be emitted by material in terms of bunches of energy. That it is not something that has a continuum value of energy, but rather is, and I will use the term, quantized into packets of energy. This was totally unusual because it's based only on a hunch by Mr. Planck. However, if he assumed that, in fact, as this, that the energy of a bunch is proportional to the frequency of the light, which is again another unusual thing because when you look at Maxwell's equations, its energy is proportional to amplitude. You know that if you shout very, very loud, the amplitude of the sound wave carries more energy than if you don't. He said, no, it has to do, the energy carried by this bunch is related to the frequency. Not to go into too much details, The first observation led to the invention later of quantum mechanics, and this one led to the invention of what we call special theory of relativity. So what I would like to do now is essentially to go into some of the consequences and try to explain to you, when we say we have what's called a special theory of relativity, what are its implications to our everyday concept of space and time. Seem to be going back and forth, and okay. So the consequences of the constancy of the speed of light, and this is something you can read in Hawking's book, is that in fact what we think of as space, which is kind of rigid as a platform within which physical events go, is not quite as rigid as we expect. So what we call, for example, a distance of 1 meter, if you measure the distance between 2 points and say it's 1 meter or 2 meters or 3 meters, someone else who happens to be passing by at a very high speed looks at the same 2 points using the same meter stick, will measure the distance between these two objects, will find in fact that the distance is not 1 meter, that in fact it would be 90 centimeters. If he's moving a little bit faster, it could be 80 centimeters. A little bit faster yet, he could shrink it down to 10 centimeters. So the measure of a distance as a result of the special theory of relativity depends on how fast the experimenter or the observer is actually moving relative to the things he or she are observing. It's not that they are using different instruments. The two people who are doing the observations could be using the same meter stick, they agree to use it, the same clocks, the same everything, except that one accelerates and starts moving very fast, and then they start making differences in the measurements of a space interval. The phenomenon I mentioned now is called space contraction. So someone who's moving very fast will see distances in the direction of his or her motion contracted, and they can become actually much, much smaller than someone who is standing still next to these objects and then making the same measurement with the same instruments. They are both correct. Neither one is wrong. On the other hand, if you take essentially a clock and take two events, you shine light at one point and then turn it off, shine the light again a little bit later on, someone watching the light, standing still relative to the light, will measure a time, let's say, of 50 minutes. Again, the same observer passing very fast relative to the light source will measure the difference, and instead of measuring 50 minutes, he or she may measure 60 minutes, 2 hours, maybe a whole year. Again, the amount of time interval that they measure between the events will depend very much on the speed with which the observer is actually moving. Again, both are correct, because primarily the main difference between them is their relative speed to each other and their relative speed to the events that they happen to be observing. What this tells us that, in fact, one of the main consequences of the special theory of relativity is that we never look anymore at space as absolute, nor as time as also absolute. That is, time and space intervals are measures that depend on the person who is actually taking the measurement. Both are correct, because both know how, if I find 50 minutes and the observer finds, let's say, 3 hours, we know that we are correct, because I say, aha, you must be traveling at that kind of speed, because I can transform from my 50 minutes to his 3 hours by knowing how fast that person is actually going. So time, therefore, is relative, and space is relative. What happens also as a consequence of this is that the concept of energy is extended to mass, and one of the most famous formulas that I'm sure you've heard of is this E equals mc squared. That becomes also a consequence, because when you try then to compute the energy, the momentum, that is mass times velocity of an object, you find that in order to get consistency again, the energy should not only include things like what we call kinetic energy, the 1/2 mv squared, but also it should include mc squared, which is an innate energy which is intrinsic into the mass content of every object. So basically, therefore, as of the year 1905, when Einstein wrote his special theory of relativity, the concept of physicists that relates to space and time changed drastically. So we do not look at space and time as absolute. However, they are relative and malleable, and therefore the structure of space distances and time differences are therefore a function of the person measuring them. Two people traveling at different speeds relative to one another can measure different space intervals and different time intervals, and they are both correct. So this is a major change from pre-1900 physics, and is something that has become part of what physicists do every day. And as you can see, this is nothing new. This is old, and it is now close to 110 years old. With the realization that space and time are not absolute, another thing came about, and that is related essentially to the concept of gravity. So let me go to other slides and come essentially directly to gravity. This is some mathematics to describe how you can transform from one frame to the other, with beta being v over c, the velocity, and so on. So this is for those of you who are in physics or in science who can maybe take this to heart and try to understand it. I mentioned time dilatation, which is the idea that you measure time as longer than what one who is at rest would measure. And space contraction is that you measure space distances as smaller than what someone at rest would actually measure. This is not magic. This is reality as is understood now. And it's not just reality theoretically. This is something that is experimentally measured, experimentally investigated, and is seen essentially every time. And especially when you do experiments with particles that travel very fast compared to the speed of light. I'm sure you've heard of the CERN Hadron Collider. Their particles within that tunnel are moving at speeds very, very close to the speed of light itself. So all these phenomena had better be taken into account. Otherwise, you can't construct anything, you cannot do anything, you cannot do any experiments with them until you implement these results and take it into account in doing the experiments. So the basic result that I wanted to pass on to you here is that there is no absolute space-time. So space-time is a relative thing that people measure as they move around in it. So momentum and energy are that, and then we get E equals mc squared. Okay. One of the consequences of relativity then also is the existence of what we call antimatter and the discovery of antimatter. So antimatter is not a matter of movie fiction. It does exist, and we have here a particle called the positron. It's the same thing as an electron, but has positive charge. As you all know, the electrons are things which have negative charge, and they are abundant in atoms. However, a beam of light, represented here by gamma, which is the Greek letter, can actually split and produce an electron-positron pair. A physical phenomena like this can happen. Energy transforms from an object that has no mass to two objects that have mass, and in this process, energy is conserved, provided that you include E equals mc squared for each of the massive particles. On the other hand, you can also have two of these, an antiparticle with a particle colliding together. They'll disappear and produce light. So the creation, annihilation of matter immediately follows again from special theory of relativity, because once you associate energy to mass and mass to energy, then this can be exchanged with other forms of energy, as in this case we have what's called pair production, and in this case we have pair annihilation. Now, what is general relativity? General relativity is trying to understand what we call the force of gravity, or what Newton called the force of gravity. There is a very important principle that Einstein thought about and in some sense inspired his, if you like, reinterpretation of gravity. And the idea is the following. If you imagine somebody in an elevator carrying, let's say, a ball, and if the elevator is at rest, if you drop the ball, you'll see the ball just fall down, as you would do it if you're standing here. However, let's imagine the case of an elevator which is freely falling in space. So you launch an elevator to outer space, and you allow it to fall on the Earth. And suppose now the person in the elevator takes that same ball and tries to drop it in the elevator. What will you imagine will happen? Is that the elevator is falling, the person in it is falling, also the ball is falling. So the person in the elevator can look at the ball and it's falling with him or her. So if he doesn't know that he's falling towards the Earth, nobody had told him that he's been launched and thrown down, he would say, the ball is at rest relative to me, it's not accelerating, therefore there is no force acting on it. On the other hand, someone sitting on the Earth observing this elevator falling down says, wow, both of them are falling and the force of gravity is acting on both of them. So who's correct? The guy in the elevator says there is no force because the ball is not moving relative to him. But the one on Earth says there is a force, and he calls it the force of gravity. So what Einstein realized is that what one calls a force of gravity to another is the same as being in what he called an accelerated frame. So the situation of this person in the elevator is that he's accelerating actually. He's not moving with constant velocity. He's accelerating. And so someone who's accelerating does not see the force of gravity. So being in an accelerated frame somewhat cancels to him or her the force of gravity. This is what is known as the equivalent principle. So let me give you another example. Suppose we imagine now that we don't live on a flat plane. Suppose we live somehow on the surface of a sphere. Now, if I ask you on the surface of a sphere to move in a straight line, according to Newton's laws, you move in a straight line, constant velocity, there is no force acting. But on the surface of a sphere, especially if the sphere is very huge, you don't realize you are on the surface of a sphere. So you keep moving. As you know, on a surface of a sphere, the straight line is what is called a great circle of the sphere. So it's a circle that actually is on a plane that cuts into the center of the sphere. You're not aware of it, you're just moving on a straight line. But in fact, you are moving on a surface of a sphere and you are moving in a curved path. Okay? If I am in outer space observing you, I don't see this sphere. All I see is that you are moving on a line which happens to be curved like this. So to me, if I'm not aware of the fact that you are moving on this curved surface, to me you will appear as someone moving in a curved path. And from elementary physics, I will conclude that there is a force that is forcing you to move on this curved path, and we call this a centripetal force. You're being pulled to the center of the sphere in order to move on this path. Now for you, there is no force acting on you. All that's happening to you is you're moving on this circle. To another observer, the fact that you are moving on a curved path, they would interpret this as you are being subjected to by a force. So this idea said to Einstein that maybe there are no forces, but that in fact we all are moving in a curved space that we are not aware of, but in fact is curved. So this way, our changes in direction of motion, we might interpret as a force, but in fact there is no force. All we are doing is moving on these straight lines in this curved space-time. So he removed the concept of a gravitational force and put instead the idea that the space-time, which we now know is not absolute, could actually be curved, and that we may be living in such a curved space-time. And he wrote equations which will define how the space-time will curve if you put matter and energy in the space-time that we have. So to him, therefore, a gravitational field is a fiction. What is real would be that we live not in a flat space-time, where straight lines are the usual straight lines we think of as Euclidean lines, but that we are actually moving in a gravitational effect that looks like a gravitational effect, but in fact is something like this. So if you, for example, imagine the Earth to be like this, and you draw this fictional grid around it to represent space and time distances or space distances, what his equations will indicate is that units of distance near the material that is, in this case, the Earth, for example, are different than here. So there is a curvature. And therefore, if you put an object essentially to move around in a straight line, this object will follow the curvature and, in fact, will form this ellipse that we normally know as the orbit of a particle around the sun or around any planet and so on. So what happens, therefore, is that we interpret the force of gravity really as a curved geometry of space and time. So there is no force of gravity. All we have is that the space and time that we live in is actually curved. So that's another very important consequence. And not only is space and time not absolute, it could curve, it has dynamical characteristics, and the dynamics, the way it curves, the way things then move in it, depend essentially on what kind of objects you put in it, what kind of energy exists in it, and so on. But then, once you assume that space and time have this dynamic characteristics, well, then you can start thinking about other things. And the question that arises, is it static? Is this dynamic fixed? Does the dynamics oscillate? If you imagine space and time to be like, say, a sheet, on one side you call space, the other side you call time. Does this sheet ondulate? Does it move? Does it do anything like this? Does it expand, shrink? So one starts, therefore, thinking about the universe, which is made up of this space-time, as a dynamic physical object, and then you ask questions as to whether expanding, contracting, all sorts of questions can then be asked. In fact, one of the things that could happen is that you can shake it. Suppose some events happen somewhere, and you can shake the space-time. You can imagine then that these undulations in space-time are going to travel. They'll travel at the speed of light. And if you happen to be in the path of such a vibration, you will feel the effect, because suddenly you see distance scales have changed near you, and suddenly you see time scales have changed near you. This is what is known as a gravitational wave. And in fact, we are fortunate today to say that within last year, and only last year, the detection of such a gravitational wave was seen. So the first time that a gravitational wave was detected, which is actually a consequence of Einstein's general theory of relativity was detected only during the past year, already 100 years after the theory has been designed. And of course, it was detected only because we have better instrumentation, better electronics, better everything than they did have many years ago. The fact that the universe is not static can also be investigated. What we do is we look out, we see lots of stars, galaxies, lots of nice shiny objects. We can actually do experiments with them. We don't touch them, but we can make measurements. One of the important measurements that we can do is to ask, how far are they? And then how fast are they moving relative to us? I know that you all experience something which we call the Doppler effect. And to be more concrete, this effect is the kind of effect that you see when, for example, a train or an ambulance, we don't have trains here, so let's say ambulance, we have plenty of them, that are blowing their horn and moving relative to you. You know that if the ambulance is coming towards you, then the frequency of the sound you hear gets to be sharper and sharper. The frequency gets higher. The wavelength becomes shorter. So the pitch, we say, goes higher. If, on the other hand, the ambulance is moving away from you, it's just the opposite. The frequency goes down, the wavelength is longer, and you can hear the difference between them. This is what's known as the Doppler effect. So if you measure the change in the wavelength of the sound that's coming to you relative to the sound that would be there if the ambulance is not going anywhere, you can actually measure how fast this ambulance is going, whether it's coming towards you or going away from you. The same phenomena happens with light that is emitted by the stars. So you can look at the light coming from a star, and if the light coming from it, and as we will see later on, each atom is characteristically emitting specific wavelengths, which is the spectrum, let's say, of the atom, of hydrogen, of oxygen, and so on, you will see that depending on the motion of the star relative to you as an observer here on Earth, you will either see the wavelengths of this light all shifted to the longer side, which we call redshift, or shifted towards the bluer side, which is we call the blue shift, and this is the shortening of the wavelength. When you measure a redshift, meaning that the wavelengths are increased a little bit, you know that that star is moving away from you. If it is blue shifted, coming towards you, you know that it's coming towards you. But not only that, you can tell exactly how fast it's going away from you because you can see the difference in the wavelength relative to what, let's say, hydrogen or oxygen will emit, which is in your lab. So this is a very important, simple, straightforward tool to measure how fast things are moving either away from you or towards you. And therefore, you can see then whether the stars in the heavens are actually fixed or actually moving. The net result is you will see that most galaxies, stars, and so on are redshifted, meaning they are moving away from you and away from each other. So this is a very important experimental observation which tells us that all the heavenly objects are actually moving away from each other. And this leads to this concept of what we call an expanding universe. Now, if it is expanding now, it must have been closer to, they must have been closer to each other before. So then you can extrapolate and say, all right, I measure the speeds and how fast they are going. What if I assume they had started from someplace? When will that have happened? That is, how much time will have elapsed to me when they were all together? This leads to the idea that, therefore, all these objects came from some origin. We call this the Big Bang, and we can estimate the age, therefore, of this universe that we are observing. And the age turns out to be of the order of 13 billion years. So the current observation, therefore, not just an assumption, not just a hypothesis, it's something you measure as if you're measuring something in the lab. However, the lab here is the universe, and you find that, in fact, we must be living in a universe, and I underline the line A, in a universe, which must have started 13.7 billion years ago, and is ongoing and expanding. Well, if it's expanding, will it continue to expand forever, or will it actually, at some point, turn around? Because if we imagine things that have been expanding, we know that somehow they're attracting each other due to the curvature of space-time. So maybe they will slow down and then start contracting again back to this fixed point. The issue of whether the universe will continue to expand or will expand to some point and then contract again depends mathematically on how much mass there is in the universe. As it turns out, if one can get an estimate of all the mass that we see, meaning the mass that is emitting light, electromagnetic waves, all sorts of things, we find that this mass is hardly 2% of what is needed to bring the universe back in. However, recently, masses that do not radiate have been discovered, because all you see is something moving in a circle in kind of empty space. So you have to assume that there is some material in the middle there that is causing it to move around it. And this material is known now as dark matter. The estimate of this unknown matter is of the order of 30% what is needed. Curvature can also happen because there is energy in there. And one also measures how much the expansion is, and surprisingly, one finds that this expansion is accelerating rather than slowing down. That it's not just expanding and then slowing down as it goes out, but rather expanding faster and faster. So there must be something pushing things apart. This we call dark energy. So they are called dark matter, dark energy. They are said to be dark because basically we know nothing about them. So although we know a lot about the universe, there's plenty of matter that we have absolutely zero idea of what it is made of, what it interacts with, what does it do. All we know is that it's out there, and we can see its so-called gravitational effect, but nothing else. Now, along with all of this, I jumped from 1900 by introducing the quantum of radiation, but didn't say much about it. Then special theory of relativity, general theory of relativity, observations of cosmology, to the idea that we have an expanding universe, and therefore we can think of an origin of the universe. So in some sense, this part of the story is that the origin, development, future of the universe has become basically a physics problem. It is a physics problem like any physics problem you deal with in the lab. And any question you want to ask about it, any result you'd like to investigate, is dealt with nowadays as essentially a problem in physics. But along with this, there were other developments in physics, which I think is important for your general education, and that is what we call the quantum nature of physical law. So the second part of the talk is going to concentrate on this, and I don't have much time for it except about 10 minutes, but nevertheless, this is beyond what Mr. Hawking wrote in the book you're supposed to read, so I'll go a little bit fast and give you at least a general idea what are the basic principles of this. Now, one of the main problems with classical physics was seen early on when you try to understand the structure of an atom. It was earlier discovered that an atom which is neutral has a nucleus which is positively charged and has these electrons that run around it. Well, I say run around it. Well, one way you can think about them, as people started to think about them at the time, which is the early 1900s, to use an orbital model like the Earth, the Sun, and so on. So we can do that. Except Mr. Maxwell doesn't like it, because as soon as you say an electron is moving around a proton in an atom, Maxwell says, well, it has to radiate electromagnetic waves. But if it radiates electromagnetic waves, it loses energy. If it loses energy, it comes closer to the nucleus, and then at the end, the atom will collapse. So if I take Maxwell's equations, if I take Newton's laws, the fact that electrons and protons are charged, and I assume some kind of orbital model, I cannot understand why atoms are stable. If I cannot understand why atoms are stable, then of course I don't understand everything that exists around here, including us. I mean, we are made of atoms and we seem to be stable long enough, actually. Okay? Quantum mechanics was introduced in 1925 by Heisenberg and by Schrödinger to essentially try to understand how to describe the structure of an atom and understand all its behavior without necessarily having to use the classical electromagnetic theory of Maxwell, or in fact, the classical Newtonian mechanics. We already saw that Newtonian mechanics has to be drastically changed, because space and time are not the same for all observers. Gravity is a curved space-time. So this is not unusual then when you go down to the sizes of atoms, that the laws of nature may be different than the laws of nature that we experience at our size of distances, which is of course where Newton's laws came from. So what Max Planck did to say that electromagnetic waves has a fixed energy, he introduced the concept of a photon. Classical electromagnetic waves, they were then interpreted as streams of these photons. And electromagnetic interactions then are between charges and these photons, and they are instantaneous reactions. Light emitted by atoms and molecules comes in specific frequencies, as I mentioned earlier, and therefore every atom has its own atomic signature. Now, short distance physics tells me that I have to abandon the idea of an orbit, for example. If I'm thinking of the electron going around the proton, it is not moving in an orbit, but I know it's there. What quantum mechanics tells me, therefore, is that you do not know where it is. There is a state in which it occurs. You cannot describe it by an orbit. All you can say that it has a specific energy and specific other characteristics. And that an electron in an atom can exist in different levels of energy, and it can jump from one to the other, and when it does jump, it leads to the emission of light. In other words, if I ask, but where is the electron? In terms of my classical approach to say I like to know where it is, what quantum mechanics tells you is that if you look for the electron, somehow you want to shine light on it and interact with it, then you can find the electron anywhere around the atom. But if you look at a specific place, you can find it there maybe with 10% probability. If you look somewhere else, it will be another 10%. In a third place, 5%. In a fourth place, 50%. So what quantum mechanics tells me is that whereas I cannot say where the electron is at all times, it tells me what is the probability by which I will find the electron in a specific space in the atom. So what turns around is that the orbit disappears, and what comes about is a description which is basically statistical in nature. And this applies actually to all physics at very short distances. So if I look for a nucleus which has protons and neutrons, and I ask the question, what is its energy? I know that I can have a nucleus with specific levels of energy. The nuclei switch from one to the other, emitting photons. We call them gamma rays because they are of higher energy. But you never know where anything is. So the classical description we are so familiar with at our size distances disappears, and all we can tell is that if I look for something, I will find it with only that probability. This is the only predictability of quantum mechanics that it can tell you. So it gives you the likelihood of the system to exist in one place or another, and classical quantities are not as well known as we assume to know in ordinary observations for things at our distance scale. So relativistic quantum mechanics, as I said, leads to antimatter. Then we find that we have lots of particles. After that, we find that interactions can be described as individual interactions between particles and photons. And then the net effect is that we get a whole interaction as a result of many individual processes. We also discover that beyond electricity and magnetism, we have, and gravity, which we have now interpreted as curved space-time, we have two other forces. One is called the nuclear force. This is what keeps protons and neutrons together in a nucleus. And it's a much stronger force than the electromagnetic force. And there is another one, which is called the weak force, which leads to an atom switching character. The character is, for example, you may have carbon-14. It can, on its own, in about 15 minutes, on average, switch to nitrogen-14, emits an electron, and what we call an antineutrino. This is a process that involves neutrons in the nucleus, where a neutron can switch to a proton and so on. So not only is mass related to is energy related to the mass of the object, but objects like neutrons, protons, and so on can switch from one to the other. The one stable particle that does not switch, luckily for us, is the proton. The proton is a very stable particle because it is a little bit lighter than a neutron. Whereas a neutron can move, become a proton, the proton cannot become a neutron. This is good for us because this means hydrogen is stable. And if hydrogen is stable, the nuclei are mostly stable. And as a result, we exist to study all of this and talk about it. Now, as it happens, we have lots and lots of objects that make up matter in the universe. Beyond protons and neutrons, there are other particles out of which the protons and neutrons are made. They are called quarks. There are things called leptons. The leptons are the electron, but the electron has another cousin called the muon, and the muon has another cousin called the tau lepton. There are neutrinos. So once you start investigating, you will find that there are large numbers of fundamental objects in the universe that make up this universe. The quarks come in 3 colors, and there are 6 types of them. So at the end, you end up with what we call the standard model. The standard model tells me that there are fundamental numbers of particles out of which everything else is made. So in some sense, in this past 100 years, we have discovered the Lego set of nature. In other words, the fundamental objects, I'll call them the Lego particles, which you can put together, and by putting them together, you produce everything else, of course, including us. So in some sense, therefore, leptons and quarks are there. Then they interact with each other. They interact with particles we call the weak bosons. These are massless, and gluons. These massless particles then become massive because of something else. And I'm sure you read in newspapers about what's called the Higgs particle. The Higgs particle enters here to give these W plus, W minus, Z0 that are massless some mass. That's a long story from here, but I think it is only important that you see that these things are well understood, they are well investigated. These are tracks in detectors that see them in accelerators, such as the one in Geneva. And we can see then how protons, antiprotons, etc., are made up of these quarks, up, up, down, up, down. So it's sort of like there is a chemistry at the level of these particles. And so the structure of the atom is that the quarks make up the neutrons and the protons. The neutrons, protons make up the nuclei. The nuclei then have electrons around them. We get the atoms. The atoms combine to form molecules. The molecules combine to form proteins. The proteins are us. And so here we are. So these are pictures of these fundamental objects of nature. And this is my final slide, which tells us effectively the history of our universe. The idea is that there was a big bang that took place some 13 billion years ago. The universe started expanding. We start with this soup of the particles I just mentioned, these Lego sets. As the universe expands, clearly as it expands, its volume is bigger and bigger. It will cool down. Cooling down means that the average energy of these particles is becoming less and less. Then they start interacting. They start interacting and they combine here. And this is a time scale. And you can see that we kind of come probably in a small sliver sort of at the end. So the universe existed for 13.7 billion years before we showed up in some sense. If you remember, we are told that dinosaurs essentially were extinct some 60 million years ago. And when the dinosaurs were around, we were not around. In fact, the only mammals that existed after dinosaurs were mice. And it's not very comforting to know that maybe we are the descendants of mice, but nevertheless, this is what science tells us. And you can see the universe has existed for many, many years before we kind of showed up towards the end here. And it is remarkable that, in fact, only in a period of 100 years, 150, the age of AUB, from 1866 to now, all of this information was put together by these creatures, that is us, and we are fortunate to effectively get the intellect and the awareness of all of this, because we are unique in this sense on this planet at least, and we tend to understand all of this. And really, when you come to think of it, you may look at this and see it's very complicated. It's really not. Once you get to know it, it becomes easy, like everything else. And to a large extent, the whole thing is built on a simple Lego set made of leptons, quarks, and some particles that they interact with. And then the rest is us. Now, where we go from here, your guess is as good as mine. But hopefully, we will not destroy ourselves by hand, so to speak, before seeing what comes about from this point. So hopefully, we'll have another billions of years to survive. The sun, which is the star that we revolve around, is known to have only another 5 billion years of life, because not only do we understand the universe, we understand how the stars evolve. In 5 billion years, the sun, the earth, and everything around it will disappear and scatter into the universe. In fact, the material that will scatter into the universe will be collected by other stars and will form other planets and so on. And in fact, you may not know this, but we are the product of elements that were formed in stars that have gone through their life cycles and exploded and were collected around this current star that we live around, which is called the sun. So the elements we are made of, the carbon, the oxygen, the calcium, whatever, was made actually around other stars that have lived their life and exploded. So in the final analysis, we all are the sons of a star. And we presumably also will eventually end up being the parents of other stars and other creatures and other things in this universe. Anyway, I hope you get a picture of what has happened conceptually, what has happened in the general understanding in physics in the last 100 years. And hopefully you, all of you, will contribute more to this physics as you live your lives. And in another 50 years, you can give lectures and tell a younger generation what has happened in the meantime. Thank you.